distance range. So that I will come later to geometrical spreading and inelastic attenuation, maybe after 2 weeks or something. Yeah. And so you will see that up to 50 kilometers, like sometime it is 40 also, but usually in the near distance range, the decay with distance is faster. That is, we call it body wave decay. So body wave, theoretically, it was explained that it is 1 by r. So the way that has been plotted, I'm not sure. I think he has plotted only y-axis as log and x-axis as linear. But if you see, if you plot both distance and the amplitude also in log, then you would clearly see this linear relationship. And in the beginning, like as I said, up to 30 to 50 kilometer range, it's the body wave regime where most of the peak amplitudes are contributed by the S waves. But when you go beyond that, beyond 50, 60 kilometer, it is surface wave magnitude. Mostly the peaks are contributed by the surface waves. In that case, the distance decay is 1 by r, square root of r. So it's slightly lower. So the further you go, you will see that surface waves amplitude decreases less with respect to distance in comparison to body wave. So there are two distance decay regimes. So this is one explanation. Another is that they didn't had so much data. So you don't know actually if there are some variation with the radiation pattern, that in certain direction the amplitude was decreasing sharply in comparison to another direction. So that we call radiation and directivity effects. But in this case, I would still say that theoretically it is 1 by r, but some people have observed it going up to 1.3 also, like 1 by r to the power 1.3. So it is really like r is decreasing very fast with distance. So people are still trying to understand why it is more than 1. So theoretically it is expected, as I will show you, that it is 1 by r. But if it goes significantly higher than 1, like 1.3, 1.5 or 6, then this is not yet explained actually, right?
Okay, sir. Yeah. And sir, one more thing I wanted to ask was the transfer function which is used to convert the seismogram from to Wood Anderson. So generally when we plot transfer functions in like geotechnical engineering for ground response analysis, so the transfer function comes in a way that it peaks around the predominant frequency or the time period of the strata of the local site. But the transfer function which we saw was like it became constant after a
Yes, that's good. Actually, even if you see the single degree of oscillator transfer function in geotechnical, like that peak you see, right, at the natural frequency, that peak can be damped if your damping is very high.
Okay. Yes.
I would say it is still the same. But the damping may be very high in that case. So they have designed the damping it in such a way that, like, rather than looking like this, so usually in single degree of freedom case, most of the time you would expect, this is the question of Sukrit, that for a mechanical oscillator, because Wood Anderson is also a mechanical oscillator, so if this is plotted in log scale and this is also plotted in log scale, so this is the natural frequency of the oscillator. So at natural frequency, usually those who are from civil engineering and physics background, I think they would see that at least if you have seen forced vibrations, those who don't have a physics background also, like at least in BSc, you must have studied forced vibration or forced oscillations. So that peak is the condition where when F becomes Fosc. So that's what we call the resonance peak, right? But this resonance peak can be damped actually. If you increase the damping, then you can make it look like somehow this, depending upon damping. That's what I'm thinking. But you are right, because it should be like this, because it's mechanical oscillator, so it should be like this. So it must be damping.
Okay, okay, sir.
Yeah.
Thank you.
Okay. So today, if there are no more questions, is there any? I can take one more question. So did anyone try to see the source spectrum part, which at least this figure I am talking about now? This figure. Did anyone try to see this figure? It is in the book, Stein and Weissessen's book. I told also that it is from section or this figure. You can find it in the paper, in the book. Because this figure is very important figure to understand why at larger magnitudes, ML, surface wave magnitude, body wave magnitude, underestimate the actual size of an earthquake. So those who have already studied that ML, MW, ML, MS, and MB, those all are not used in core seismology anymore because they saturate at higher magnitudes. Now, if you want to understand why they saturate this, then you should have seen this picture. Anyway, I will try to explain it. As much as you can understand, it's fine. I do not expect that you understand this point, this figure at this moment, because I will try to explain it later also. This figure is essentially the source spectrum of an earthquake, theoretical source. Like you can see it from the observations also, but this is at the moment plotted theoretical. This one or this one. These are called source models also. Like if you plot, if you have the time history of an earthquake close to the source, like at 10-kilometer distance, for example, or 1 kilometer distance, you have corrected it for the distance decay and inelastic attenuation because amplitude is decreasing with distance. So if you account for this decrease with distance in the amplitude, then when you plot its Fourier transform, it will look like this. So that is what is the source. What I mean is the source spectrum. Anyway, so first we want to start from here, where we left is that we discussed that we have, other than ML, we have ML. Keep in mind that ML was measured on a specific type of instrument. It was designed for California by this guy, what is his name, Richter, and originally it was referenced at 100 kilometers. So he meant by that whenever you will measure earthquake at 100 kilometers distance, that will be its magnitude. So one could say, and why not at 1 kilometer, or as Gunjan was asking, why not at 10 kilometer? So it's his choice that he decided. I don't know from which region. Maybe, as I said, one of the reason is that maybe he had most of the data at 100 kilometers. So he took this reference as 100, or he thought it is a better balance between 100-kilometer distance is somewhere in the middle of his data. Like he had the data up to 200 or 300 kilometers, and he thought that 100-kilometer was in somewhere in the middle of this. So he chose a reference of 100 kilometers. So, and other than that, we had a body wave magnitude. In body wave magnitude, we have two versions. One is smaller, you write M and with B in small cases. And when you write B in this large cases, then it is a different, it is still a body wave magnitude, but the way how it is measured. So in case of when it is B is smaller, in that case, you consider only first 5 seconds after P wave arrival. So if this is your P wave arrival, this is your like noise floor. Suddenly an earthquake comes, your P wave is, first wave is P, primary wave. So your P wave is arriving at some point. So P wave is a body wave, right? So they start from the onset of the P wave. So we call it onset. So when the P wave is hitting your seismometer, so from the onset of your P wave, they decide or they select first 5 seconds and then the peak amplitude of from those first 5 seconds, right? So it can correspond to a certain frequency range. So that is how, and then you take the log and then you make the distance correction as you are making in case of ML. That is how you measure this MB. If you consider the entire body wave part, so you have to find the onset of the P wave and the end of S wave. So where your S wave is finishing, because after S wave there will be surface waves. like love wave, Rayleigh wave, they will arrive after S wave. If you are far away from the source, if you are very close, you may not have surface waves. We will discuss this thing. So when you consider the entire body wave part, and you consider a certain you consider a signal which has a certain period, so that period is again varying between 0.5 second to 12 second. Period means when a particular oscillation takes the time. uh, Period is the time when one oscillator takes that much time to complete one oscillation. So that is what I mean. And then they consider the peak of that, and then they divide this peak divided by the period of the corresponding wave, and then take the log and make the corrections. So that is how MB, and similarly MS was also computed like this, that in a case of MS they consider the surface wave part corresponding, and they find a wave which has a period of 20 seconds, around 20 seconds. That means it is taking 20 seconds to complete one cycle, and consider the maximum amplitude of that cycle, and then divide it by t. And I asked one question: what is the point of dividing it by t? Can anyone guess?
Sir, because velocity is a better parameter to represent a intermediate time period.
Yes, this can be one thing, intermediate, but they wanted to relate it to energy.
So it might change the rate of that change in velocity.
Yes, no, their point was more energy actually. So they thought that velocity is more related with the energy, kinetic energy basically, half mv square thing. So we will come to this also. Now from after magnitude, we will discuss earthquake energy. It's a very interesting topic. So that's why they divided, because A was the displacement. So if you divide displacement by time, so it will be essentially velocity. And they thought that this is better representative of energy. So that was this. Then another magnitude scale was moment magnitude. So as the name suggests, it is related with moment. So before going to that, whenever there is a fault breaks there, or once, as we discussed in last class also, that you have, whenever you have a rupturing, you have it sort of like this. And now a question, Abhi, did you find the answer of that question? After looking at this figure, I just got reminded. You were asking one question that day.
Yeah, actually I saw, sir, but I could not imagine I could not. I understood what he is trying to say, but like we say, no, intuitively I could not draw the diagram in my mind. Like how is this? Like compression is happening diagonally and dilation is happening in the figure here also in this slide.
Mm-hmm. So did anyone else read it? That how the these are dilation and how these are compression?
I think that this was related to the location of the station with respect to movement. So if the
Yes.
movement takes place like the towards the station, then it would be compressional,
Yes.
and it would be, if it moves away from the station, then we term it a dilational wave.
Yes.
Or
Yes. So, but his question is like how they form a quadrant thing. Like the compression is in one diagonal and the dilation is another diagonal. So how they form this? So to understand this, just imagine this sign, what I'm trying to show here, that when material is like the two sides of a block are moving like this, so you just can imagine that this side is pushing the material this side. So this is more compression on this side, right? So you just make it like as a quadrant. I will make it as a quadrant. So if this is my actual fault plane, for example, so if this is my actual fault plane, the blue line, right? And this side is going in this direction. And this side is coming in this direction. Okay. So when this side is moving in this direction, so it is basically trying to push material in this direction. So let's call it compression. So when it is pushing in this direction, the upward direction, So the material, when it is pushing here, so you can imagine on this side there will be dilation. Similarly, when it is pushing at this side, so there will be compression, and because it is pushing towards this direction, so somewhere here there should be dilation. So the same, so that is what we are assuming, that this is happening at the fault. And the same process, if you imagine that this is as pressure thing, so the same process one station should record also. That's what the point is. If you are very close to the, if you put your seismometers close to the fault, not only close to the fault, like 100 or 200 kilometers, so the pressure information should give this information also. P wave should give this information that the material closed in certain directions, like for example in this direction and in this direction, the station should feel a pressure. And in this direction and this direction, the stations should feel that the earthquake has taken, it's not a pressure, it's like sort of tension. They should feel sort of tension, that material was pulled away from their location. So as if the material was pulled away from their location. And these stations here in the plus sign station, they should feel that as if the material close to them was pushed towards them, right? So that is what is happening in this case. So this process, as you see, there are two forces involved here. One is in this direction, and another is in this direction. So what they are forming, we call it as a force couple. So whenever there is a force couple, so in earthquake processes, always you cannot have a single force. You cannot have a sharing with a single force, or you cannot have automatically. You can have sharing by a single force in your lab, but within the earth, you cannot have force at one point automatically. If you have force at one point automatically within the earth, that means you will see that there will be some angular momentum will be there. So angular momentum will not be conserved. That material will rotate if you are applying force from any direction. So it will have a tendency to have not angular momentum. It will have some momentum there. But within earth, momentum cannot come from zero anywhere. So suddenly there is a zero momentum, and suddenly you cannot have a momentum. So in order to balance, there is always actually two forces, and these two forces are acting in opposite direction. So they form a couple. So that couple is also formed, if you remember, when we have a case of moment, right? How do you define a moment? Like usually you have seen, if the force is acting, one force is acting here, one force is acting here, this is F1 and this is F2, and these two forces, the axis of these two forces is a distance d apart. And then you simply write F into d. If F1 equal to Fd, F1 equal to F2, you simply write moment as Fd, right? So the same thing is happening here in case of earthquakes, that these two opposing forces, they will create a moment, right? Now the question is, will there be only one couple? If there is only one couple, like this, if there is only one couple of forces acting, what will happen? What will happen?
Rotation will happen.
Rotation will happen. Yeah. Exactly. If there is only one couple is there will be a rotation, right? So the angular momentum is not conserved. But whenever earthquake occurs, we don't see rotation. We mostly see shearing. So in order to keep the momentum conserved, so that material close to this is not rotated, you will have an opposite moment. I don't know how to draw this opposite moment now here. So its tendency is in this direction to rotate it in this direction. Same couple you will have, so that it is just to balance it, so that there is no rotation. So the model of earthquake, if you read this, any book of seismology, they will always say double couple. There cannot be a single couple. All the observations so far, they are observed with this, and the model to them is that there is always double couple involved. If there is a single couple, that will involve rotation, right? So that's why in case of earthquakes also, there is a moment. That moment is defined as seismic moment. You can try to relate it with F into D also. This mu is the modulus of rigidity. This D naught, sometime people will write it D bar also. Okay. This is the average displacement on the fault. Average displacement, that how much. So if two blocks were like this in the beginning, so after the earthquake, how much they have on an average moved at each location. So the movement at different locations will be different, right? But on an average, what is the total displacement after the earthquake is called this D naught or D bar. Mostly in the books you will see D bar, so use D bar. And A is the area of the fault. A is the area of the fault. So you can see this will have units of moment. How? Because you can write stress as, I can write, sorry, I don't have some space to write here. Shall I write it somewhere in a different note? Or maybe I have written it somewhere. Yes. So moment is force into displacement or the distance. So this force can be written as stress multiplied by area multiplied by D. This stress you can write in terms of how you can write mu, because modulus of rigidity. So you can stress you can write in terms of strain, right? So you will find that that is how this relationship between, so stress is proportional to strain. So suppose there is some strain. So yes, this strain is, so the stress will be essentially mu into some strain. We can call it D bar, suppose, right? So you can write your M0 as mu into D bar into area force. So this was stress, this was area. So I think that is how you can compute. I'm not able to find it exactly how it came, exactly how this is derived, but if you check the units, actually the point was that it's the units. So these units are of either Newton meter or dyne centimeter. So this you can check. Usually it doesn't have, I think, any derivation. M0 is doesn't have any derivation, but it has units of moment. So I was trying to find if there is some derivation for this, but we can have still a derivation, I think. uh, uh, so the derivation is again with respect to a double couple, I think. So as I said, so initially this was the fault location. After this, one fault has gone this, so this is D. So as you said, this is one direction force, the other is like this. At the same time, to stop the rotation, we should have one force in this direction and another force in this direction. So we should have a double couple. So this is one force, equal and opposite. This is another force. Okay, so this is one, actual fault is this, motion was in this direction. Since to oppose this motion, we should have equal and opposite moment. Equal and opposite moment. So this is the, so if I say this is the force, so actually it should be D now. This is F1, this is F, this is F, and the displacement is D. So that is how, and then you can write it in terms of stress multiplied by area multiplied by D. area is coming because stress is force per unit area. So stress area and D is there. And yes, stress multiplied by stress is proportional to strain. Mu ds. This is area, this is your strain. Stress divided by strain is mu essentially, or is it other way around? Strain divided by stress or stress divided by strain?
Shear stress divided by shear stress.
Yeah, we are talking about modulus of rigidity. So shear stress.
Yes. Stress
So,
by strain.
yeah, stress by strain mu. So how can I write? So stress will be it should be stress should be D into mu. Yeah, I'm not sure actually if this is correct, but I will try to find it. I usually there is no derivation for m0 as far as I know, but this is the definition that it has a unit of moment, either Newton meter in MKS system or it has dyne centimeter in CGS system. Or you can try to find out also this definition, or I will try to find it in the next class also. Okay, so that is how we define a moment. So the important thing to understand about the moment is that it directly depends upon the displacement, that amount of average displacement that has occurred at the source, and on the fall dimension, that is through area. So that is how m0 is defined. So that means m0 is giving you an idea of that how much on an average displacement has occurred on the actual fault, on the place where your earthquake has occurred. And it is also proportional to the size of the fault, like how big is the area. So it is multiplied with the area multiplied with the displacement. So if the area is like 100 kilometer square in comparison to 50 kilometer, if an earthquake has if a fault has 50 kilometers 50 square kilometer area, so that earthquake will have a magnitude smaller moment. So the total amount of moment released is mu average displacement and A. Now we are coming to some interesting questions, that why earthquake magnitude is saturating. So moment is defined as modulus of rigidity, multiplication of modulus of rigidity, average displacement D, area of the fault. So that is how moment is defined. So people usually, geologists can go on the field, they usually go and they can measure this quantity. So in case of earthquake, this is one of the quantities. I think there are not any other quantity which we can measure on the fields in terms of earthquake, because most of the other things are measured through the seismogram. But this is the quantity. M0 is the quantity that you can go on the field, you can see there how much slip has occurred, try to compute those slips at different points, and then compute sort of an average slip, and then multiply it with the fall dimension. So you will come up with a moment. So moment is always related with the actual size of an earthquake, that how much rupture has happened, how much slip has happened, and how much was the dimension of a fault. So this gives you the actual size of an earthquake. Now, that's why people said that, I will come to this, that there should be a magnitude which actually decides the actual size of an earthquake. Other than that, ML was measured from the seismogram, MS was measured from the seismogram, MB was measured from the seismogram. And all these three magnitudes were measured in different frequency ranges. They all correspond to different frequency ranges. MS corresponds to a different frequency range, ML corresponds to a different frequency range, and MB corresponds to a different frequency range. What do I mean by this? That they are measured by the signals in the seismogram corresponding to different periods. So they have some specific period. Whereas this M0 is measured from the field. One way of this is measuring that you go to the field and you measure the actual size of an earthquake. So they measured this M0 for different earthquakes. For example, so for San Fernando earthquake in 1971, so this was your M0. So this was your M0. The MS for this was 6.6. San Francisco earthquake, which was bigger than that, M0, as you can see, there is at least of the order, the difference of the order of 10. So 5.4 multiplied by 10 to power 27. So I think these all are in dyne centimeters. MS, the surface wave magnitude was 7.8. Alaska earthquake was 1964. You see the change in now M0. The factor is now 100 because this is 10 to power 27, this is 10 to power 29. So that much difference is there. The biggest earthquake on earth so far recorded was having a moment 10 to power 30, and the change in order is 1000 because this is 10 to power 29. You can see here 10 to power 30, sorry, 1. So from 29 to 30. So the moment is larger here and the moment is smaller here. Is smaller here. MS is telling you 8.4 and MS here is 8.3. So you can clearly see that M0 is for Chile earthquake is larger by a factor of at least 10. But your MS is giving you a value 8.3 in comparison to 8.4 of Alaska earthquake. And the slip in those earthquakes also, because this is telling you some slip thing. So the slip was here 7 meters, the average slip, G bar. This is D bar, average slip. Here it was 21 meter, but still MS was giving a lower magnitude. So that's what people said, that for in case of large magnitudes, like beyond magnitude 8 usually, that surface wave magnitude is underestimating the actual size of an earthquake. So actual size of an earthquake is related with the total amount of slip, because it is essentially the slip, that how much slip has occurred and what was the actual dimension of the fault. That is being underestimated by MS. Some people call it magnitude saturation, but better term is that underestimation, right? So the question is, why do they saturate? So if MS is saturating, MB and ML, they also saturate. They saturate even before. So if your MS is saturating somewhere at magnitude 8, your MB will start saturating at 6.8 already. Or ML also around 6 or 6, between 6 and 7. So they start saturating before. So the question was, why do they saturate? So as I said, MB seldom gives a value above 6.7. The other version, the capital, this version goes, I think, 7 point or 7.6, 7.5 or 7.6. So if you are measuring it with the first 5 seconds, then it doesn't go beyond 6.7. The maximum magnitude it can give is 6.7 or 6.8. So why do they underestimate? What causes the saturation? The important thing is, just as I said, that M0 is the true measure of an earthquake size, because it is mu d s or mu dA, where s is the area, or you can write it mu dA. This is essentially same thing, area, because it tells you that how much moment has generated there. And we will see that this moment is actually related with the energy also. How we will see this? I will show it later. So the moment is essentially telling you how much the actual size of an earthquake. And the actual size of an earthquake depends upon the area, that how big the fault was and how much the slip that has occurred there. So on a smaller fault, there can be a larger slip also, right? So it's not necessary that only larger faults are generating the larger slip. Of course, they have more space to go. Larger faults will have, if a fault is 100 by 100, so it has more space to slip. If it is a smaller, it will not have that much. But the relative, if you take the percentage, so smaller fault can also rupture or slip more. So smaller earthquakes means, so if you see, as I said, so smaller earthquake means the slip is smaller, so the D will be smaller for them, and they have a smaller area usually, right? And whereas the large earthquake rupture larger areas, and one important thing is that larger earthquakes generate more smaller frequency content. This we will see from the source spectrum also, and you can imagine that when a larger earthquake is breaking, so it will try to generate signals with longer wavelength also. Just you can think it in terms of like if there is a large scale feature somewhere, so a large scale feature means the wavelength is large. So when the wavelength is large, it means the frequency is smaller. And whereas those smaller earthquakes, they generate more high frequencies. They do not generate low frequencies in the signal. Right? This is important to understand. This we will see from a modeling perspective. I can show this from a formula and from a model also, but physically you have to think that smaller earthquakes are rupturing smaller areas. So they are like very fast, a smaller portion like a small firecracker or something, you can imagine it like this, that a small firecracker has gone. But a big earthquake is like, it's not like a firecracker, so it's taking some time. It's taking 10 seconds, 20 seconds, 30 seconds, or in some cases 1 minute also to completely rupture the fault. So it has some large scale features, so it has a wide range of frequencies. I'm not saying that it will not generate higher frequencies. It will also generate higher frequencies, so don't get me wrong that larger earthquake is not generating high frequencies. What I'm saying is that the larger earthquake will generate more smaller frequency content or more smaller frequency information in comparison to smaller magnitude. We are talking about smaller frequencies. So the size of the fault and the wavelength of motion are very important. So what happens, because why these magnitudes saturate? These magnitudes are saturating because we are measuring them at a certain frequency. The scale which we are using them to measure, imagine, because we are measuring, in case of body wave, we are measuring when the frequency is, I think I have written it somewhere, when the frequency is in a certain range, 0.5 to 12 seconds. So as I said, for MB, we are considering it somewhere when the period of the signal is 0.5 to 12 seconds. So it is around 1.5 is around 2 hertz to somewhere 0.1 by 12, 0.9 or 0.8. So around 2 hertz, we are measuring it between somewhere 1 to 2 hertz or 1 to 3 hertz. So we are using a signal from the earthquake because earthquake is generating signals of different frequencies. So larger earthquake is generating more smaller frequencies, whereas smaller earthquake is not generating smaller frequencies. Let's call it like this. It generates high frequencies, but it's not generating low frequencies. Now what is happening? The instrument or the scale which we are choosing to determine earthquake magnitude, from those all available signals, we are using only signals with having certain frequencies. So for example, in case of MB, we are choosing those body wave magnitudes, those body waves whose period is lying between 0.5 to 12 seconds. That means we are choosing a wave with a certain frequency. Similarly, in case of surface wave, we are using a period of 20 seconds. So 20 seconds means 0.05 hertz, right? So we are using a particular wave. Now this is the problem. The main problem is that we are using a particular wave with a particular frequency. So now when your fault, now you see we are using a particular wave frequency, mean wavelength, right? We can convert frequency in space by f equal to v lambda, or f equal to v lambda, right? Or f lambda, other way around. So small fault, if the fault is very small or relatively small compared to the wavelength which you are using to measure it, it's just like optics. So if you want to see an electron, you cannot see electron with this normal light, right? It's the same thing in optics. So the wavelength should be comparable or of the order of the dimension of the material which you want to see. In case of electron, you need an electron microscope, right? So you need whose wavelength is very, 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 very small, right? So in case of small faults, when the wavelength is smaller in comparison to, or is of the order of the same dimension of the fault, you can easily measure the size of the fault. But now your fault has become very large, and your wavelength is small. So what will happen? Fault has been very large, like 100 kilometer by 100 kilometer, for example. It will not be 100 by 100. Let's call it 200 by 30 kilometer. 200 by 30 kilometer. And your wavelength of the wave which you are using to measure the earthquake size is 20 meter or 30 meter or 50 meter. So can that wave of wavelength 20-30 meter, can it see the entire fault? No. The wave, you will still need a bigger wavelength to see the entire fault. As I said, that the fault dimension or the wavelength of the wave which you are using to see that fault, just imagine it as a microscope, because we are using different frequencies, different we are using signals of different wavelengths. So if your fault is very big and your wavelength is small compared to that fault, you will see only a portion of the fault. You will not able to see the entire fault. Physically, it is like this. Imagine it from the optics, what I am saying. So what you will be able to see is only one portion of the fault. So that means for bigger earthquakes, MB, MS are using, in their measurement, are using smaller wavelengths in comparison to the earthquake size. So that means we should use even smaller wavelength to actually have the actual size of an earthquake. They work for a smaller magnitude because smaller magnitudes have a smaller size of the fault. And the wavelength which we are using to measure and the size of the fault, they are comparable. So that in that case, we can easily measure the size of the earthquake. But when the fault has become very big in comparison to your wavelength which you are using to measure the size, in that case, that fault which you will see, you will not be able to see the complete fault. What you will see is only a portion of the fault. So that's why they underestimate. So the actual earth size is 100 kilometer by 30 kilometer, but your wavelength is giving you a size of, for example, 70 kilometer or 80 kilometer because of this issue. That is how it is physically from the concept of optics. But now, if you want to see it from a modeling perspective, this model is also physics-based model, but it is easy to understand here rather than saying it in terms of words. So the source spectrum. So I want to use a different page now. Additional notes on magnitude scaling. That's why I said this is slightly difficult portion now. So I will show it when I will discuss source part also. So whenever you have an acceleration trace, displacement trace, we are talking about displacement. This is your time. This is your displacement. Let's call it U. It is varying with time. So that is how your seismogram is recording. So if you take its Fourier transform, some of you might have heard it, Fourier transform. I will discuss this later, what is Fourier transform. So usually with the frequency, it looks like this. It has a corner, FC. So in this direction, it is frequency. So there is a corner, and here is the amplitude in this direction. And this point, this low frequency, when f is tending to 0, the amplitude of your Fourier transform at f equal to 0 is directly proportional. So I'm writing it amplitude directly proportional to m0. Seismic moment. So amplitude when f is tending to 0. So f is tending to 0 is this. F is tending to 0 means very low frequency. It cannot be 0, but it can be like 0.0001. So very low frequency, or we can say it is DC, sudden offset like this. When a wave is like this, so when f is 0, it's just initial and final. So there is just an offset. So this, when the frequency is tending to 0, so this is a source spectrum. I will explain it later, but I will come to this saturation part again. But you should try to understand it or read it about it. So this is when f is tending to 0, the amplitude of your Fourier spectrum is directly related to the seismic moment which you observed from geological measurements. This is very important. So that means the 0 frequency amplitude. 0 frequency is, just imagine in your mind, what do you mean by 0 frequency? Physically, try to think about it. What do we mean by 0 frequency? Think it in physically. Like a permanent offset is a 0 frequency thing. If that is moving it like this, then there is a wave of certain frequency. But when it is a DC component, it's directly this. So it is already giving you information of displacement that has occurred on the fault. That there is a permanent displacement, 0 frequency information. So this amplitude is proportional to m0, and m0 you already know is mu ds. This is also giving you again the size of an earthquake. So that means if you want to measure the actual size of an earthquake, you should measure it when f is tending to 0. For any earthquake, whether magnitude 3, for magnitude 4, magnitude 6, magnitude 8, magnitude 9, magnitude 10. When you will measure it at f tending to 0, at very, 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 very small frequencies, your magnitude will never saturate because it will always be capturing m0. Essentially, we want to catch m0 because m0 is giving you the size of an earthquake. But what is the problem happening with ML, MS, and MW? We are measuring MW at 1 by 20. We are measuring MB at 1 by 0.5 or 1, for example. So that is 2 Hertz or 1 Hertz. So if we are measuring them at a frequency which is not close to f equal to 0, that means there will be a problem. How this problem will come? I'm explaining it now and try to see it. This is my corner. I said that this amplitude, this plateau level amplitude, because it is same over f less than c. For f less than c, if this is f, this amplitude is giving you m0. So whether you take it at f equal to 0 or you can take it at f less than fc is also fine. But what will happen if your you are measuring, suppose your this is your 1 hertz and FC is 0.5 hertz. Okay. This is your 1 hertz and your FC is 0.5 hertz. So that means, why I'm saying it 1 hertz, because you are measuring MB at 1 hertz. So when you are measuring it at 1 hertz, you are not measuring it here. So what amplitude you are measuring? You are measuring this amplitude. So, and you are defining your magnitude from this amplitude. MB is measured at 1 hertz. Let's say it is measured at 1 hertz. Your corner frequency is FC is 0.5 hertz. Right? So that means you are measuring a smaller magnitude, because you are not measuring this M0. M0 was this. You are measuring this. If you take it on the y-axis, it is somewhere here. Now, so that is why it is getting saturated. That is why it is measuring, giving you a smaller magnitude for large earthquakes. MS you are measuring at 1 by 20, that is 0.05. That's why it is very small. 0.05 is already very small. That's why MB saturates first and MS saturates after that. So MB is saturating around 7 or 7.2 or 6.8, between 6.8 to 7.2, and MS is saturating around 8, 7.8 and 8. Because we are measuring it at even further lower frequency, that is 0.05. As I said, if you are coming towards F tending to 0, the better you are measuring your magnitude. So now your MS is measured at this hertz, this frequency. In case your FC has become 0.01. So what has happened? So this is 0.01 and this is 0.05 at which you are measuring MS. So still you are measuring a smaller magnitude, because actually it should be here. Actual M0 should have been here. But what your MS is giving you this, right? But if your FC is still 0.5, just I'm giving you different scenarios. If your FC is still 0.5 and you are measuring MS at 0.05, that means you are measuring it somewhere here. So you are perfectly fine, because you are capturing basically the this asymptotic amplitude where F tending to 0. So you are still on this flat line. So as long as you are measuring in this flat line zone, your magnitude will not saturate, because you are essentially capturing M0. But as soon as you are capturing it beyond this corner is very, very important in seismology. Very, very important. If you are measuring beyond this corner, that means you are measuring it here, somewhere here. If you are measuring it here, somewhere here. That's what this lecture is showing you here. Kahan gaya? That's what it is showing you. Same thing. So it is showing that larger the magnitude, the corner is shifting towards higher frequencies. Lower frequencies. The corner is shifting towards lower frequencies. So your MS is fine here, because MS is in the plateau. 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 Now MS is no more in the plateau. MS is on the right hand side of the corner frequency. That means it is underestimating now. Actual magnitude is this. Actual values are this. MB in most of the cases, MB, see, here it's fine. Here it's not fine. It's already on the other side of the corner. It's not in the flat zone. So MB will start saturating from already 4.345. This. It already started saturating here. So that's why these magnitudes saturate. I will discuss it again when source models will be discussed. Particularly, I will discuss this portion, that I discussed about MB and MS. What is the problem with W? Local magnitude. So this I am giving as an assignment. Explain why ML saturates. MS and MB I have explained. Now all of you have to prepare one page, only one page answer. You show me, you don't have to, you can write in terms of some definition, some language, whatever physical inferences, but you have to show me by using this figure and by using this figure that what is the problem, why ML is saturating. So I will post this as a assignment. I really want you to make, I really want to make sure that you understand it. Use this figure, concept from this figure, and concept what I just discussed. And I can give 2 weeks for this assignment. But you have to make me understand that why that is saturating. Everyone has to prepare this. And if you want to discuss with your colleagues, you can discuss, but not with the Shikha and Shreyasvi. That why these magnitudes are saturating. MS and MB I have tried to explain. Even if you have not understood, tomorrow we have a class, you ask me this again, I will explain it again. That I have not understood what you were telling. Or this source part I will explain when I will discuss source spectrum again. The same thing I will explain again, but for 2 weeks I want that, because within 2 weeks I will finish the source model part. So within this, I can give you 2 weeks. You have to give me answer why ML is saturating. We have discussed MS and MB. So from M0, Hanks and Kanamori in 1979, they gave one new magnitude scale, which is called moment magnitude. So you can clearly see this magnitude is directly proportional to M0. So moment magnitude never saturates because it is based on the seismic moment, which is essentially proportional to the size of the earthquake. So different names are there, so that portion you can read. And why use moment magnitude? It is the best single parameter of overall earthquake size. It does not saturate. It can be estimated from geological observations, as I said. It can be estimated from paleoseismological studies, and it can be tied to the plate motions and recurrence relations. And it can be estimated from the seismograms also. So there is one student from Iran here, Mehran Dawadgari. So he has been estimating it for Iranian earthquakes. So you can estimate it from the seismogram. So he has seismograms and he's doing inversion and getting M0 from those seismograms. So you can estimate it if you have a seismogram. And it is also interesting. People have done some studies, like they have tried to plot M0 against the fault dimensions, earthquake moment magnitude essentially. So they tried to plot. So there are empirical relations between earthquake magnitude and fault dimensions. So if you know the area of a fault or a length of a fault, you can calculate empirically. So these are some empirically means they took some observations and then they tried to fit some straight line or a quadratic straight line or something like this. So they tried to observe some linear or this sort of relationship between earthquake size and moment magnitude. The moment magnitude they estimated was from the seismograms, and the size of the earthquake they estimated from the geological field measurements. So they went to the field, they took the fault dimension measurements and moment magnitude measured from the seismogram, and then they tried to come up with some empirical relationship. So that's why it is also useful. And now you can see that MW is 9.3 for this Sumatra earthquake. For San Francisco earthquake, it was 7.8, 6.9, 6.7. So it never saturates, because you are essentially, how it can saturate? Because it is basically you are computing it from the source dimensions, M0, which is based upon the source dimension. And you can compute it from the seismogram also. So the bigger the rupture, bigger is the moment. So this figure is telling you the saturation. So on this side is the moment magnitude. As you can see, this is moment magnitude. These are different magnitudes. So the first one saturate is MB, then ML, then the capital MB, then MJMA is Japanese meteorological magnitude scale. Last one is the MS. You can imagine why MS is the last one, because it is already, we are already measuring it at very low frequencies. But certain earthquakes, corner frequency can be smaller than 0.05 second also. If the corner frequency is smaller than 0.05 second, means you are not measuring it in the plateau range. What I'm talking about. You have to measure it when the displacement spectrum of your Fourier amplitude is flat, in that range. So essentially that you measure it at very small frequencies, 0.01 or 0.001 frequencies, then your magnitude will not saturate. So this portion is done. We will discuss it tomorrow again, and then we will discuss, I would like to discuss about magnitude, energy and intensity part. So this portion is taking some time, but it's fine, because there are very interesting things in magnitude, because it is, people do not pay so much attention to the earthquake magnitude, but it is a very important topic, and it is still ongoing research topic. And I found a problem with, when I was preparing for today's lecture, I found one interesting research problem with this relationship, which I was checking, Hanks and Maguire, this relationship. This is very, very often used relationship in seismology between seismic moment and earthquake magnitude. But I'm sure that there is some problem. And this we will discuss in tomorrow's class. Thank you. I think we took already 1 minute extra. You might have some next class. See you tomorrow then. And please see that lecture again. Otherwise, it will be difficult, as I told you. So I will stop recording. You can leave now.